Hello, welcome to Fresh Concrete. This is one of a series of online talks produced through partnership between the Building Centre and the Concrete Centre to showcase some of the innovative uses, manufacturers and new types of concrete that are emerging, many of which are being developed to address the climate mitigation and adaptation needs of our built environment today. My name's Elaine Tugard. I'm Head of Architecture at the Concrete Centre, and I have had the privilege of helping to select the lineup of presenters and presentations that we have for these events. It's been fascinating. It's also been a really challenging process to select the subjects that we're going to feature. There are just so many exciting projects and products and processes being developed that we could choose from to feature in this series, all of them bringing fresh approaches and fresh thinking to concrete. So we hope that you find this presentation and you find the series as inspiring, interesting and thought-provoking as we have. So the subject of this Fresh Concrete event is carbon sequestering concrete. Now by that, I mean innovative industrial carbonation technologies developed to enhance and accelerate the carbonation of concrete. Now you may know carbonation is the naturally occurring process in which concrete absorbs carbon dioxide, permanently removing it from the atmosphere over its lifetime. Now, all concrete does this, but the rate depends on the type of concrete, the conditions to which it's exposed, and its design. So in steel reinforced structures, carbonation is designed to be limited to protect the steel reinforcement in there. And you can see from these images some samples of concrete in which the carbonation process is being tested. The grey concrete around the outside is fully carbonated. That is, it's reacted with the carbon dioxide in the atmosphere and permanently locked it into the concrete there. But the pink has yet to carbonate. And much of it is unlikely to do so, actually, until that concrete is eventually crushed or crushed for use as recycled aggregate. And it's at that point then that those new multiple surfaces of that internal concrete, shown in pink there, that they're now new surfaces are created and then newly exposed to the atmosphere, and so accelerating that carbonation process. So it's well understood, this process of carbonation, as a technical design consideration for engineers. The carbonation of concrete has, however, recently been recognised by the IPCC, that is the Intergovernmental Panel on Climate Change, as an important carbon emissions sink. And the UK government has also recognised that this process needs to be accounted for in its greenhouse gas emissions. And so it's commissioned research to develop a robust method to assess the role of concrete in the absorption of carbon across our whole built environment. And actually, we're only the second country in the world to explore this after Sweden. And so as a result of this research, it should help to improve the accuracy of UK greenhouse gas accounting. So that is a short summary of the natural process of carbonation of concrete, in order to provide you with a bit of context about carbonation in the UK today, and a bit of context for the following presentation by CarbonBuilt. Now, this is one example of new technology that's been developed to enhance and accelerate the process of carbonation, and it's often called industrial carbonization. Or industrial carbonation. In other words, permanently locking in that carbon as part of the manufacturing process. So earlier in the process. The CarbonBuilt were joint winners of the NRG Cozier Carbon X Prize in 2021, together with CarbonCure. They're the focus of another Fresh Concrete recording. Each demonstrates a different way in which concrete can be manufactured using carbon dioxide, reducing both the embodied carbon of the concrete, but also permanently locking in captured CO2 emissions. Deployment of their technologies to avoid and reduce carbon emissions was described by the judges of that competition as a game changer for global decarbonisation. So I'd like to introduce you now to Cindy McLaughlin, and she will be joined in the Q&A after the presentation by Connor Cooper, Head of Business Development for CarbonBuilt. So over to you, Cindy.
Hi, I'm Cindy McLaughlin, Head of Product from CarbonBuilt. Thank you so much for having me here today. I'm going to go ahead and share my screen. Hope you can see this okay. So CarbonBuilt has a technology that reduces the carbon footprint of concrete products by anywhere between 70% on the low end and over 100% on the high end. While we're tackling the whole range of concrete products, we're starting with hollow block, as you can see here. And critically, we do this without compromise. So we don't compromise on price, block performance, or plant operations. As you probably know, today concrete products include somewhere between 10 and 15% of the cement ingredient, which is a very bad, highly emissive ingredient, and they're cured with steam. CarbonBuilt actually replaces entirely or substantially reduces cement. We add in a little bit of hydrated lime, which can either be virgin material or a waste material. And we add additional waste cementitious materials that are carbon reactive. Then we go through the same process, but on the back end, instead of curing with steam, we cure with dilute carbon dioxide. And we do it at moderate temperature, at ambient pressure. So there's not a lot of energy expended in this process. We can get the carbon dioxide from a bunch of different sources. It's all waste. So we can get it directly from flue gas, which can be very dilute. We can get it from biomass waste, which may be agricultural waste. It may be wood chips from a local lumber yard. Or we can get it soon from modular direct air capture, where we're actually pulling carbon dioxide out of the air. We circulate the CO2 in the curing chamber for the block. And through this process, we absorb the CO2 into the block and mineralize it into calcium carbonate permanently. The effect of this is that we reduce the embodied carbon by 70 to over 100%. So what you're looking at here is the carbon footprint of a traditional block. That's the baseline. And you see much of that comes from cement, and with a little bit from the aggregates in the manufacturing process. These are actually two different formulations from our first commercial plant, which should be coming online in Q1 of 2023. Formulation 1 has a lower total carbon reduction. So we're using virgin hydrated lime here. So we're only reducing the carbon footprint by about 82%. But a slightly higher percentage of utilization, so of mineralization into the block. So in this block, just over 2% by mass is calcium carbonate or mineralized carbon. In formulation 2, we get a much better overall carbon reduction. So we hit 102%, and just under 2% is mineralized carbon. And we play around with mixed designs to get the best performance of carbon reduction and price. And of course, our blocks are what you would expect. They're all industry standard. So they qualify for ASTM C90. We had additional performance verification done by the National Concrete Masonry Association to make sure that things like stress strain and shrinkage and flexural bond strength were all up to par. We also had a third party called 350 Solutions come in and test the carbon reductions that we said we could make. Much of this third-party testing was in the run-up to the NRG COSIA Carbon X Prize, which we won in April of 2021. So how does it actually work? We integrate with existing block plants. So we do not create the blocks ourselves. We work as a technology provider. We collaborate with block producers and we set them up with the retrofit. So you can see here at the front of the plant, there's a CO2 processing skid, which brings the carbon dioxide to the right humidity and the right temperature. There is some piping in the curing chamber, which allows the CO2 to circulate correctly and make sure that all sides of the block are cured. And then we've got an extra silo here for additional raw material storage for the hydrated lime. Now we share in the capital expenditure to retrofit a plant. So in British pounds, you can assume it would be something like 750,000 to just over £1 million British pounds for a single production line of a single plant. And we share that CapEx. We then are margin accretive. So we grow the margin of the producer in two ways. One is through raw materials cost reduction, because we're using hydrated lime, which is generally a widely available commodity. We're using lower cost additional cementitious materials. And then the curing process is not particularly high energy. Secondly, we can bring an additional revenue stream through the monetization of the carbon credits because of the substantial reduction of the carbon footprint. So we monetize two different kinds of credits. One is the avoidance credits from reducing or eliminating cement. And the second is the removal credits from the mineralization process. So we take those out to the voluntary carbon markets and we bring that revenue stream back to the producer and we share in the margin accretion. And we do this in lieu of licensing. So we never charge a fee to the producer. One note, in the UK, there may be additional revenue opportunities from tax credits or other things that are built to incentivize conversion of plants to make low carbon stuff. So we try to be good for everybody in the value chain. We can work with local power plants or other heavy emitters, and we are a pretty low cost abatement option for them. We work with concrete producers to save them a lot of money and bring them new revenues. So there's somewhere between 4 and 8 British pounds per ton of concrete that we can gain them in revenue. And then for concrete customers, we give them a very low carbon or no carbon block and with no other compromises. They should pay the same price that they're expecting to pay and the performance of the block should be the same. So just a little bit about our company. We were born out of the University of California in Los Angeles's Institute for Carbon Management. The foundational research for CarbonBuilt happened there from about 2014 on. We've got a bunch of patents and more coming. CarbonBuilt spun out of UCLA in November of 2020. So this company was set up to commercialize the process that had been built within UCLA. And between late 2019 and early 2021, we did scale demonstrations. So we created about 15,000 blocks between 2 plants in Wyoming and Alabama, both of which were cured from local power plants. One was a coal plant, one was a natural gas plant. We worked in collaboration with the US Department of Energy for those 2 pilots. This was in the run-up to the Carbon X Prize, which we won in April of 2021. And because of the transparency and rigor of the X Prize, we had a whole bunch of third-party analysis done. And so, as mentioned, we did performance analysis, we did some economic analysis, and we also did our carbon reduction analysis. From late 2021 through present, we've been focused on commercialization. And so we've been bringing in revenues from the sale of our carbon credits. We've been growing the team. We were excited to sign an agreement with Master Builders, which does admixtures. They've been working with us on our future product pipeline and bringing new admixtures to the table. We were about to be able to announce our first retrofit contract, and we've been expanding our pipeline across the US, but all over the world. So we've got conversations going on in Europe, in India, and in Canada and throughout the US. Thank you so much. I would be happy to answer any questions you may have. And my colleague, Connor Cooper, who's our head of business development, who's been running the Old Castle APG Anchor group, would also be happy to answer questions. You can email me here, and thank you so much.
Fantastic. Thank you very much. Short and sweet, and lots packed full of information. Thank you very much, Cindy. So I don't know if Connor, you would like to join us, or maybe you can chip in if you feel you need to. Up to you, Connor, hiding there in the background. Thank you very much. So it's really interesting to see this technology being applied specifically to block work. And one of the questions we've got there is its potential application for other forms of concrete. I noticed there was a slide there at the end you had with some hollow core floors, it looked like, not sure, or even ready mix. I'm not sure. So tell us a little, explain that a little bit more. What's the scope of the potential application?
Sure. So we're starting with block, but we've got an R&D pipeline that should be able to handle other concrete products in the not too distant future. So segmental retaining wall, tiles, pavers, floor wall. And you know, the carbon uptake may be a little bit different in some of those other products, but we're working on them.
And so presumably the surface area of your product is an important part of the efficacy. I noticed that the block itself that you've used and that you kindly shipped over to us to show off at Future Build this year is a hollow block, but it's not limited to that, presumably?
That's right. So the surface area is important. You know, so curing will typically go a couple of inches in. I think, you know, that earlier slide that you showed that showed the curing process sort of coming in from the outside. That is true with our process as well. So, you know, products that have less surface area are going to be sort of lower in the list of priorities for us. Connor, is there anything you want to add?
Sure. Hey, everyone. Glad to be here, chipping in on the questions. And I think the only thing I would add is, you know, we're kind of, I think Cindy highlighted, we're started with block. That's where a lot of our R&D came from. So we're very confident and comfortable with the technology and how it applies to those products first and foremost. But as we build out the pipeline, not only are we evaluating other products in terms of how we apply our technology, but we're also continuing to look at how things like admixes can come into play to help us penetrate deeper or to increase the CO2 uptake. And we recently announced a collaboration with master builders specifically to do that, and kind of enhance our R&D side of things to ensure that we're able to build out the product portfolio more broadly in the coming years. Excellent,
thank you. And the type of blocks that you're using, so we talked about the form of the block and the surface area. Does it make a difference whether it's from a dense aggregate block, medium aggregate block, and a more open, lightweight, or aerated block type? Do you want to talk a little bit about that?
Sure. Cindy, you want me to jump on that one? So I would say, you know, I can't speak to aerated as much as the other questions because I just am not unaware of much research we've done on that side of things. But when it comes to lightweight, medium weight type block, you know, very determined by the aggregate that we're utilizing rather than something that's kind of chemically happening. We've tested with a variety of different kind of aggregate sources. There's nothing that changes about the aggregate. We're really just changing a kind of the chemical reaction that creates the binding and kind of creates strength. So whether it's lightweight, medium weight, normal weight, there's no concern around kind of that spectrum of products when it comes to the block. I think the bigger thing would be, you know, thinking about kind of blocks in the UK, there's there's more solid blocks, and then there's the kind of hollow blocks that we're talking about that are probably more equatable to what we're doing in the US with kind of a typical 8816 block that you'd see in the States here. So I think, kind of drawing that equivalent, that's probably where a lot of our focus would be if we were looking at products in plants in the UK in particular.
Thank you. So is there any limit then, do you think, on the maximum compressive strengths that's achieved, or is that again really linked to the aggregates?
Yeah, I'll field that one as well. So I think no real limit. I think the limiting factor is going to be what sort of level of impact we can have. And I think that's when we think about a standard 8816 block and what we're trying to achieve, we're looking to try and match performance, kind of like what CarbonCure was talking about, not trying to overshoot and kind of make this a performance story as much as we're trying to make this a kind of sustainability carbon impact story that kind of combines with some cost savings to have return on investment, and also kind of positions us to go to market at price parity, which we think is really important to have impact. If we're trying to ask for a green premium or some sort of making it a niche product in some way, that's different than making it the standard. And that's really CarbonBuilt's goal, is to evolve plants so that we're producing with a little different methodology and kind of making this the 80-90% of what a plant would make using CarbonBuilt technology versus more traditional cement and kind of heat and hydration curing. Hopefully that answers the question.
Yeah, I think so. Yeah, thank you very much. So we've got a few more questions here as well. I think there's an appetite to drill in a little bit more into the process. So does the CO2 get added into the mix? Or is it only during the curing process? I think I know the answer, but I'd like you to answer that.
So it's only during the curing process. Our mix designs, and we create custom mix designs based on what's locally available and what's cheap. So, it could be, we use as many waste materials as possible. And then on the back end of the process is when we introduce the CO2.
Yeah. So that's where it's the enhanced curing process there. And using the technology and the equipment, we're not using the technology, but using the equipment typically that you would have within a block manufacturing. So they typically have a curing chamber, presumably you'd be working with that, or is it slightly different?
Yeah, so as you would imagine, a lot of different variations in terms of block plants and kind of curing chambers and curing processes. So, we're trying to work to customize with any of the folks that we're talking to, and kind of take a case by case approach to how we modify any sort of a kiln setup. I think some of the key things, in terms of how we look at the curing process, we need to have good, consistent gas distribution. I think there's a question that popped up around kind of how blocks are arranged on pallets, and assuming we get good gas distribution, there's no issue with kind of consistent curing across the pallet. And so that's a key thing with any sort of design, and making sure we get good gas circulation and air circulation through the chamber. But we've done a number of different pilots on that, and kind of operational, kind of showcased in an operational setting, and we feel good about kind of how we're going through that process to ensure consistency. And obviously that's an important piece.
Excellent, thank you. Does it impact on the curing time? The time that those blocks need to be in the chamber?
No, I think that's a unique approach, and Cindy said it early on in the slides. I think there's three big things that we're really focused on. We don't want any sort of impact to the product performance, impact to the plant performance, and want to ensure that we're having kind of good impact when it comes to any sort of the sustainability goals we're trying to achieve. And as I think about I came from actually CRH. And kind of the APG division within the US after spending 10 years there. I would say that if you impact, kind of any of those two pieces kind of related to the plant with product performance or plant performance, it's a non-starter. And I think that there's been a lot of time and energy put into the research to ensure that those weren't going to be, impacts that would prevent adoption. And then, and obviously we mentioned going to market at price parity is also important in terms of kind of reaching the level of scale that we want to reach to be able to have a broader impact.
Thank you. And I'm wondering if either of you are able to talk a bit more about the sort of quantities of carbon dioxide that could be absorbed during that curing process. It's, as I think I understand it, it's a two parts of the process, isn't it? One is the actual mix of the concrete, and one of them is the curing, and they both help to reduce the carbon footprint. Do you want to talk a little bit about that?
Sure. So on the front end, we can significantly reduce or even eliminate the cement component, which takes down much of the carbon footprint. And then on the back end of the process, when we cure with CO2, you can imagine sort of 3/4 of a pound per block. And I think it's about a 34-pound block. So, Connor, do you know how that would translate?
Yeah,
leave everybody their calculators out.
I think that's it too. So we have that same challenge where we all think in U.S. terminology to some extent, but I would say, the reference to about 2% mineralization is a good one. So when you think of, kind of if you've got a 1,000 pounds of kind of concrete, or call it 100 kilograms of concrete, you would be mineralizing somewhere around that, that 2% level. So it could be 2 pounds per, or 2 kilograms per 100 kilograms actually becomes mineralized. Now, when you think of the overall impact, however, there's the combination of avoiding CO2 in terms of the carbon footprint plus the mineralization kind of yields a much larger number, where you're seeing somewhere in the order of magnitude, I would say generally 3 to 5 times what we're mineralizing, we're also avoiding. And that comes back to what Cindy was showcasing around, what are the inputs we're able to use. If it's a virgin hydrated lime, it's going to be a little lower total avoidance than if we're able to use kind of what I'll call is a lime derivative of some sort that's kind of already gone through a process and we're using as like a residue type material. So at that point, we might see, 5 times the impact in terms of kind of avoidance, and you combine those things together, and it's a really meaningful number that we're taking out of the equation.
Thank you. And we have one question here. Somebody doing a bit of good due diligence, where they just talk about historically hydrated lime has been partly phased out from a health and safety point of view. And of course, it's always an issue with anything that we're doing or any innovation. Is there anything specific, or is there any new issues that need to be thought about with regards to that, or precautions?
No, I mean, I can't speak to the global viewpoint on hydrated lime or kind of lime residues as to how that they're handled. I will say, much like cement, this is handled in a similar manner. We're not looking to have any of it escaping in terms of that supply chain. So it's, handled very similarly in terms of the tankers. It's put into silos as a powder. From there, it's kind of enters your batching system. Everything's pretty closed in terms of the overall kind of handling and operation of what you see, much like cement. I don't think anyone wants cement dust escaping into the air, and there's obviously health and safety concerns related to that as well. So I kind of view it somewhat similarly, and it's a widely available product, at least in the US, and I believe there's a number of different lime producers across Europe and other parts of the world as well, and that gives us some confidence in our supply chain as well, where we're not relying on a niche material in terms of how we can expand.
Yeah, and it is done in quality, it's in a controlled environment. That's the difference between how it would have been used historically. This is in an industrial process that obviously has all the necessary health and safety associated with it. So on that note, what about availability, talking to partners within the UK and Ireland, a bit closer to home, to our home? Yeah. What? So,
given my role within the organizations, talk to a lot of producers, and we're having those conversations, on a global scale. I think there's some large and kind of industrial manufacturing players that honestly produce at a global scale. So we're in dialogues with them, as well as kind of producers or across the US, which is more our home base. Cindy had referenced that we have our first producer that we're working to bring online in the Southeast. So, you know, we're early in the commercialization process, which is, you know, exciting to be kind of on this journey and definitely, you know, with kind of line of sight of delivering some significant impact, but we're still early, looking at a lot of feasibility studies and kind of building out the pipeline. And obviously we'd love to look at that on a global scale, especially with some of the, I would say, legislative pressures and you know, kind of other countries beyond the US, as much as the US is kind of seeing sustainability as an increasingly important issue. I think there's a lot of
Absolutely.
so excited to have those conversations on a global scale as needed.
Absolutely. The door's open. Yeah. Excellent. Thank you very much. I'm afraid that's all we're going to have time for now. And thank you to all the questions that have been asked, of course, to Cindy for her excellent presentation and Connor for answering those questions.